And make sure not to miss the final, right? It's being pushed on us. But instead of starting at 9:45, we will start at 10 a.m. Because the final, you don't need 2 hours. I think 1 hour should be okay. So the 10 a.m. And I think the final is on the Monday or the final week. You have to check it. Should be in your My FIU. Okay, so last time we started to talk about stellar parameters, and there was a pop quiz question about that. The most important one is the mass of a star, and it depends on the nebula it was born from. So if you have a lot of gas and dust inside that nebula, you can get a very, very massive star. If you don't have enough, maybe you will get a smaller star. But the mass of stars will define everything about stars. Almost everything. First of all, it will define its luminosity. So what does it mean, luminosity? It means the oomph of a star, the rate at which it's burning fuel. So if you have a very, very massive star, you're going to have a lot of gravity that will squeeze all the hydrogen nuclei together, and they will have more motivation to fuse into helium, and they will do so quicker. Okay, so what's luminosity? The unit is watt. So it's the rate at which energy is being burned inside the core of a star. So larger star, more massive star means more power output. Okay, so it's like a high metabolism. And because those stars, the very, very large stars, have a large power output, that means they will have a shorter life. So the relationship is very easy. The luminosity, so the oomph of a star, depends on the mass to the fourth power. Okay, so that's a question always for the assignment. So it means fourth power means if the mass is multiplied by 10, the energy output will be multiplied by 10,000. So 10 times 10 times 10 times 10. Okay? So then you have temperature. Okay? So temperature means if the star is massive, okay? So everything is squeezed. So it means it's going to be hot. And the temperature is about proportional to the mass. Okay? Larger mass, larger temperature. It's about proportional too. If you have the temperature, you can define the color. And I will explain again. So for example, our sun peak in the green. It's actually a green star, but because our eyes mix all the rainbow colors together, we're going to see it like white. So it's a white star, and by the time it reaches the Earth, it's going to be yellowish because the light will interact with the atmosphere, but it will peak in the green. Okay, so if you have the color of a star, you can find its temperature. There is also a very easy relationship. So temperature is about proportional to the mass of a star, and then it will define the life. Okay, again, it's the mass to the third power. So it means if you have 10 times the mass, the life will be divided by 1,000. Okay, we already discussed that. And then more massive star will be bigger, larger, obviously, and it's about proportional. Okay, so all that will be true when they are on the main sequence. Main sequence stars, meaning they are burning their hydrogen into helium. When they're going to run out of hydrogen, they will migrate away. They will be, they will inflate. Okay, they will be, their size will increase, and they will become a red giant, like Betelgeuse, a super red giant, and that's another story we will talk about. Okay, so the relationships are very simple. So if I ask you, does the chemical composition depend on the mass? Not really. It depends mostly of the nebula it was born of, right? So, for example, our sun can have calcium, oxygen, magnesium. If the stuff it was made of had those calcium magnesium oxide. Okay, so the chemical composition will depend mostly on the nebula it was born from. Another thing that will not depend on the mass, that will be the distance, of course, because distance is relative, it's relative to us. Okay, so we talked about that. Luminosity is the energy output, and it depends on the mass to the fourth power, which is also to the temperature of the fourth power. Life of stars, the story is die hard, live young. That applies to stars. Some people do, not all of them. We have exceptions. And then remember that quote that I like, very famous quote: the light that burns twice as bright burns half as long. So it means if a star is twice as luminous, its life will be half that much. If the luminosity, the energy output, the metabolism is multiplied by 3, the life is divided by 3. So it's inversely proportional. If the luminosity, the energy, the oomph of a star multiplied by 10, the life is divided by 10. So it's easy to remember that very famous quote from that cult movie. It's a very, very famous movie. It's a dystopia, Blade Runner. And Ridley Scott is still around. That was a very old movie, 1982, but still very relevant today. Okay, and we talked about black body curve, the black body spectrum. Okay, so that was developed in 1900 by Max Planck, and it was just the beginning of quantum physics, but not quite. Just after Max Planck, you have Einstein, who proved that light, okay, sometimes will behave like a wave, but sometimes light will behave like photons, right? So little light particle, little bundle of energy. So that was quantum, the beginning of quantum physics, the early 20th century. So he developed this mathematics, which is very interesting. What it says that if you take a prism, okay, you take a prism, and that is called spectroscopy. So you look at the light coming from a star, you have a prism, and you're going to split the wavelength into, you're going to split the light into its component wavelength, right? And you're going to look at which wavelength will peak. So, for example, again, our sun is a green star, meaning it's going to peak in the green. But because all these colors are mixed together, it's going to give you a white star. But by looking at this peak wavelength, we can find its temperature. And the relationship, it's called Wiens law, and it's a very easy relationship. It's just inversely proportional. So it's not even algebra 2. Maybe algebra 1, right? Say 1 over. Okay, now if you take a very hot star, so if you increase the temperature of the star here, you see Sirius A is a very hot star, 10,000 K, and I don't know if which way here. You see it's gonna peak in the blue, even in the UV, ultraviolet. So it means it's a very, very massive star and it's a very hot star. As you decrease the temperature, so I'm going to decrease the temperature. Okay, I'm going back to the sun. And here I have a light bulb. A light bulb will peak in the infrared. Okay, so the most wavelength it's going to emit will be in the infrared. By looking at that wavelength here, we can find the temperature. So that was developed by Max Planck. So it was really 1900, the end of the 19th century, the beginning of the 20th century was the beginning of astrophysics, because we were able to apply physics, in particular quantum physics, to understand stars. And we had like amazing tools because we were able to find the temperature of stars, right? Not only of stars, Earth. So if you take Earth, for example, it's also a black body. I don't know if I have to use this maybe. Okay, so Earth will peak. I don't know if which way I have to go to show you. So anyway, Earth absorbs light from the sun, but it's going to emit in infrared. So by looking at that wavelength the Earth is emitting, we know the temperature of the Earth, which is about 60 Fahrenheit, thanks to the greenhouse effect. We, human, also peak in the infrared. So I think it's a question today in the pop quiz here. You see? If you look at someone with infrared vision, like those special goggles that the firefighters use, you can see someone shining in the infrared, and the hands and the head, that's where radiation is lost the most. Okay, so it's used a lot in the real life. For example, if you have a house and you want to make sure it's well insulated, so you will call for professionals that they will look at your house with infrared vision, and they gonna find where the heat is leaking out. And you look at that in the infrared, right? So again, as you increase the temperature of a star, it goes from orange and then yellow, and then it's going to be white, blue. You see, temperature increases, and the color will shift from red to blue. So typical question for the final: red star is cold, blue star is hot. Blue star is big, short life. Red star is small, long life. The other thing you can use, so this is called spectroscopy. Okay, so we take a prism, spread out like a rainbow to get like a rainbow, but not only for visible light. So you have a continuum here, but also for invisible light. So here you have infrared, microwave, radio wave. On the other side, you're going to have X-ray, a little bit of gamma ray with the sun, not much. So most of the X-ray coming from the sun is going to be shielded by our atmosphere. So thank God for that. Sometimes we have some gamma ray burst also being stopped by the atmosphere. We have microwave and radio wave. And then there is another mathematical tool that we can use. If you find, so here you have different wavelength, how much of this wavelength we get. Okay, so this is like intensity. Okay, so a lot of green photons, a little bit of red photons, little bit of blue photons, some radio wave photons. If we find this area here under the curve, we can find the luminosity of a star, the oomph of the star, the power of a star. So it's quite amazing, right? So if you have a light bulb, okay, and you use spectroscopy, and you can find the peak wavelength, you will find the temperature of the wavelength, but you can also find its watt, 60 watt, 100 watt. Okay, so we had so amazing tools thanks to physics to understand stars. So that was in the 1900s. Okay, so we talk about that. Okay. So if you have any question, let me know. So distance of object of stars does not depend on the mass, obviously. To find the distances, it was also developed around the 1900 for faraway stars. Okay, we use a technique which is called the standard candle. So it means if you know how bright is a star or how bright it's supposed to be, and we compare to how bright it looks, then we can find the distances. So for example, again, when they were working in 1990s to understand the evolution of the expansion of the universe, they use supernovae as standard candles. Supernovae are explosions that happens at the end of some stars, right, at the end of their life. and it goes very, very bright, and it's always the same brightness. So they were looking at supernovae very, very, very far away, just after the Big Bang. So they compared to their brightness to how dim they appears to be. So they were able to find the distances. And from there, they discovered the universe was expanding back then at a slower rate that it's expanding now. So that led to a Nobel Prize. So it was a big breakthrough. Okay, so what happened? At the end of 19th century, they developed what we call astrophotography. So photography, French. I forgot his name, but he invented photography. He was French 19th century. So then they used that for astronomy. And what they did basically is you have a telescope and just you attach a camera at the end of your telescope. So now they had access to long exposure. And because they had access to long exposure, they could, so that what you see is Orion. You see Betelgeuse and Rigel and the belt here and the sword and the nebula. So anyway, with a long exposure, sorry, you can analyze the brightness of those stars. And if you have the brightness, you have the luminosity. So they started to have access to luminosity of stars, their oomph, their metabolism, how fast they are burning the fuel. For that, they needed to have the distances, but that's another story. I will tell you how, at the same time, early 20th century, the end of the 19th century, it was thanks to a woman, Henrietta Leavitt, they found a way to find the distances to stars. One method, and then you had different methods after that. So anyway, so that was astrophotography. So what they did after that, they used spectroscopy. So they had a prism, like a prism at the end of that telescope, and they started to collect 100,000 of spectra. Okay? Like 100,000 from 100,000 stars, they will have tons and tons and tons of spectra. So at the time, you didn't have digital technology, so it was very, very painstaking. It was like you need to have a lot of patience to do that. It was a photographic plate made of glass, and they will analyze those spectra. Okay, so what does it look like? Okay, so it looks like this. So a continuum of color, like the rainbow. So they were looking only in the visible light. Okay, so at the time they didn't analyze X-ray, gamma ray, or radio wave. So here you have the rainbow colors here, and on top of it you have what I call a QR code, which is called absorption lines, which means that some of the wavelength were missing. I didn't understand why they were missing, but it was already used by chemistry to find which chemical element is in a cloud, for example. So that was already a technique used by chemistry, but they didn't understand how to interpret, like why here you have this kind of QR code or that kind of QR code. But what they knew, because of chemistry, they were able to see that if you look at those lines, you know what is inside the star. Okay, it will give you the chemical composition of stars. So, for example, if the star has hydrogen, you're going to see this QR code. If the star has helium, you're going to see this QR code. If the star has oxygen, you're going to see this. So it's like a blueprint. And if a star has mostly hydrogen, 75%, and then it has helium, maybe 25%, and some other elements. So if all of those three elements are inside the star, you combine all the QR codes. So thanks to this tool, they were able to know what's inside the star. And that's how helium was discovered, because we have helium on Earth, but it was not known at the time. So they found this element inside the sun. So that's why they call it helium, because it's named after Helios, which means sun. It's the god of sun. Maybe Helios means Apollo, I don't know. Okay, so let me show you a video to explain.
If you use a prism to spread out white light, you will see a continuous spectrum of colors.
So that's if you use a prism.
If you first pass the light through a cool gas, you will see dark lines, or
So the gas will be the atmosphere of a star, okay, the outmost layer of a star. So light goes from the core of the star, then it goes through its atmosphere, and now you see that you are missing some wavelength.
gaps in the spectrum. This is called an absorption spectrum, because the dark lines are created when the cool gas absorbs these specific colors from the light passing through. If you heat up this gas until it starts to glow, it will produce an emission spectrum, bright lines of color in exactly the same place as the dark lines in the absorption spectrum. These lines are the specific colors this gas emits when heated. Every element produces a unique set of lines, thereby making it possible to identify elements by
So if the gas is hot, right, or if the star, you have a star and you have neon inside the star, you're going to see the rainbow with those black lines. And it's used today because let's say you are inspector and you see some suspicious smoke coming from a chemical power plant, right? And maybe you think, oh, they are using mercury and they are not supposed to use mercury. So you will use a technique, spectroscopy, to look at that smoke. And you look at those black lines, you see, okay, I see CO2, okay, that's fine. I see water molecules, I see mercury. And then you can take your investigation further and you ask a judge, to go in and to inspect what's going on. Okay? And they did do that for maybe some pollutants, right? Being emitted. So even this technique is used in chemistry. So it's called
looking at
spectroscopy.
spectra. Thus, we can discover what the sun and other stars are made of by looking at the lines in their spectra. By studying these lines, we can figure out these distant objects' temperature, speed, distance, and age, among other things. If you use a
So the idea is really that light is the great informant, right? I know if I just to show you, you have to be a trained spectroscopist to really decode. It's like a code, right? So you look at this spectrum here, and if you have some skills, you can say, oh, okay, I see magnesium, oh, I see oxygen. Not only that, those lines here can move back and forth, so you can find the speed of a star or the speed of a galaxy, because you can use the same technique to a galaxy as well. If it's thicker, maybe it means you can have more magnesium. And if it's fuzzy, maybe you can find even the density of a star. So it's like a code, right? To find, like a RNA is a code for a protein. This is a code for whatever is inside the star, but much more. Okay? And if you take a chemistry class in high school, if you took a chemistry class in high school, because you're not in high school anymore, obviously, you will do that experiment, right? So, for example, they take a flame and they put some calcium in that flame, right? Or unknown, you don't know what is putting inside that flame. You look at that through a spectroscope, you see those black lines, and the game, it's like a game, is to find what is that powder by looking at those black lines. Okay, because I used to have an outreach program for kids, and that was very fun. Like they will have unknown element that will be calcium, maybe this is magnesium, whatever. Put that in a flame. The kids will look at it, at the flame through a spectroscope, and they will have to find out what is the mystery powder. So maybe you did that in chemistry. It's a very famous lab. So here is testing sodium. So you need some bright light. Okay, so that will be the light from the core of the star. So this is like your prism. You're gonna use. Okay, so you make the light goes through a slit, and you go. It's going through a prism. So you see your continuum of light. So it's very continuous. And here you're gonna use sodium. Sodium. The flame is yellow. And now you see the black line here. So yellow line means the yellow wavelength that you are missing means it's sodium. So it's a very famous experiment. So they did the chemists did develop that technique before astrophysics, right? They still the only thing is that they didn't understand what was going on, but they had this tool before, and now they were able with astrophotography they were able to use it for stars, and now they could find out what was inside the stars. But not only that, because they had 100,000 spectra of stars. So they had to find a way to classify those stars, right? Because there are too many of them, 100,000. And that was done by a group of women, very famous. They were called calculators because at the time you didn't have calculators. So mostly it was women in charge of that because very detail oriented and it was a poor low wage job, right? So they were called calculators. So this group of women were in charge of looking at 100,000 photographic plates and try to make sense of those stellar spectra. They were very famous because they were working for Harvard University at a branch of Harvard, which is called the Harvard College Observatory. Okay, and it was only women, and the guy who was in charge here, it's a man, obviously. His name was Edward Pickering, so he has a funny name, and they used to call that Pickering harem. Of course, you cannot do that joke today. That was back then, and they were all very passionate about their job, but very paid poorly. Okay, so at the time, so beginning of the 20th century, even then, and 19th century even worse, the women could not have access to higher education. It was very difficult. The only access that was possible was to go to a college just for women. So you had college just for women, and it was not available for everyone. So Harvard had a college for women. It was called the Bartcliffe College. So some of them were graduated from there, but not all of them. Okay. And of course, you could not go to Harvard University if you were a woman. The first one to graduate, to be allowed to go to Harvard University was Cecilia Payne, 1920. Okay, so you had to wait 1920 for women to be allowed to go to university, but it was not just women. People who are not wealthy didn't have access to universities at the time. So anyway, that's not my point. My point is that one of those women, very famous, her name is Annie John Cannon, and she was able, so you see the photographic plate, to sort out those 100,000 of stellar spectra, and she sort them out in spectra classes, right? So it's kind of it was a classification. So she took all the spectra and she divided them into groups, and the groups goes O, B, A, F, G, K, M, and now you have L and T. So she came up with this sentence: "Oh boy, a fine guy kissed me lovingly." And now you have a T, so tenderly. And now you have a Y, yo. I don't know, try to come up with something, but at the time it was, "Oh boy, a fine guy kissed me lovingly." Because it was not appropriate to say a fine girl. So depending on your preference nowadays, you can say, "Oh boy, a fine girl, kiss me lovingly." Okay, and she was very famous because from 1911 to 1915, so only 4 years, she was able to classify 5,000 stars, right? So then the scientists, the physicists, use her work to try to make sense of what was going on. Why all stars who were blue star, right, had this QR code here, and why G star, like our sun, had this QR code here, and why red star, like a small red star, had this QR code. So they knew the color, they knew the classifications, but they didn't make sense of it yet. They were still trying to understand what was going on. So that was thanks to Annie John Cannon, and she had a very poor health, and I think she died young. Now, before her, there was another lady, same group, that classified the stars according only to their hydrogen lights. And then she merged some and she made new classes. So we stick to her classification. It's called the Harvard classification. I don't know if I have a picture. Because when I want to look for something, of course, I'm not going to find it. Stellar classification. Okay, so you have all. So then later we understood that all stars were very hot, but they are blue star, and then you have B star, okay, A star, F star, G star, which is like our sun, and now we have new groups, L, T, Y. So, "Oh boy, a fine guy kissed me lovingly, tenderly," and there is a Y, so maybe it's yo. So L is a star, okay, it's very cool red dwarf. T is what is called a brown dwarf. So brown dwarf is a failed star. It's a star that started fusion and then stopped. And Y is also a failed star. So anyway, let me show you. So there were like 80 women. Let's go back to name. A short movie. It's a cute movie, but I like the pictures.
The awesome name Annie Jump Cannon makes me think of a Wild West rodeo star or a famous explorer sailing around the world. But Annie was an explorer of a different kind. Not only did she discover and catalog more stars than anyone else ever, she also helped create a star classification system we still use today. And she did all this while being almost completely deaf, working at a time when women couldn't vote and most women were studying sciences. Annie Jump Cannon studied physics and astronomy in college, and after she graduated in 1884, she learned photography, which was still brand new, and traveled around Europe taking pictures that were eventually published. Her life was going really well, but then she came down with scarlet fever, which made her almost completely deaf. Then things got worse when her mother died. Things were looking really bad for her, but then she got a job as an assistant to a famous astronomer, Edward C. Pickering. Pickering eventually asked her to work alongside other women astronomers who would also become famous, like Williamina Fleming and Antonia Mallory. They were called the Harvard computers. No, they weren't machines, but they were called computers because they performed calculations over and over again. Their job was to examine photos of stars taken by a giant telescope and classify what they saw. The problem was, no one had come up with a good classification system. Each woman had her own idea of how it should work, but Annie Jump Cannon came up with that brilliant idea of classifying them by their light pattern. She would look at photos with a magnifying glass and examine the light coming from the star. The pattern would tell her how hot or cold the star was. Annie was fast too. She could classify 3 stars a minute and eventually catalog 350,000 of them. That's more than anyone else in history. Annie died on April 13, 1941, at the age of 77. She was so famous for her hard work and intelligence that there are buildings and streets on Earth, a crater on the moon, an asteroid in space, and even an important award named after her. I think Annie Jump Cannon is as inspiring as the stars she studied. Thank you, Annie. Ready for my special bonus fact? On a good night, when you look into the sky, you can see about 19 quadrillion miles of space. That's a 19 with 15 zeros after it. The light from most stars you see has traveled so far that you are seeing the way they looked thousands of years ago. It's like looking back in time.
Okay, it's cute. Okay, so Annie Jump Cannon, she's the one who came up with this classification, and we are still using those again. Okay, so they are called stellar classes, right? But it was not understood what was going on, and then they use this classification, try to make sense of stars, right? And it was done at the same time with Ernst Sprung, so he was Danish, and an American here, which is his name was Henry Norris Russell, right? So what both did, they developed what we call the HR diagram. So HR diagram is like the periodic table for chemistry. So it's the most important table in chemistry. Okay, so it's a way to visualize stars, okay, according to their class and according to their luminosity. So the HR diagram, so it's named after the author, H here for the Danish, R here for the American. So they got the idea to take all the stars at the time that they knew about, and they plot those stars on that diagram here. On the x-axis, they had the classifications, right? The classes. So here will be B star or O star, so very blue. So here you have blue star, and going this way you have red star. And at the time they didn't have the temperature yet, because it was just before they developed a way to find the temperature given the peak wavelength. But on the y-axis, you had the oomph, the power, the luminosity. Because thanks to long exposure, they were able to find luminosity of all the stars. And surprisingly, you can see a trend. Okay, so this is called the main sequence. So our sun, for example, will be somewhere there, plotted there. Okay, so this here, what you have here is a log scale, meaning if you increase here a step by 2, you go from here to there, so it's a step of 2, the luminosity is multiplied by 100. Okay? If you go from 0 to 4, it will be multiplied by 10,000. So what does that mean? It means that hot star, blue star are very luminous, and then red star or small star will be dimmer. And when that will define how long they're going to live. But they didn't understand all that yet. They just saw that there is a pattern here. Okay, so that will be called the main sequence. because if a star is plotted in this here on that line, that means it's burning its hydrogen into helium. And then in this area here, you have outliers, okay? So these are called red giant or super red giant or super blue. So those stars have left the main sequence because they run out of hydrogen, so they start burning helium into magnesium oxygen, but it's not very efficient, so they will become swollen, right? They increase in size. So it's about to die. They are about to die. And when they are dead, like a sun-like star, it will become a white dwarf and it will end up here. So anyway, the thing you have to understand is that HR diagram, on the x-axis, you're going to have the spectral class. So these are big star, hot star. Over there, you're going to have cool star, red star. And the y-axis, you have luminous star. We know why now. It's just that big star is going to be squeezed more because of gravity. So they're going to burn their fuel quicker. So of course they're going to be more luminous, and that depends on the on the mass. And then here the stars that are red, okay, red star, they don't have much gravity, so they burn their fuel, but very, very slowly, and they live forever. So they're gonna be here. So that was a big breakthrough. Everyone was very excited to understand what's going on with stars, right? Same thing here. So also published around 1910, 1920. But in that case, he put also the colors, right? So you have blue star that are big stars, so they peak in the blue. And here you have red star. You have this trend here. And here you have the power output. And they were still trying to understand what was going on. Okay, so this is called the HR diagram. I don't know if I have maybe a video. So remember, at that time, they didn't understand that you could match color and temperature. So hot star will be blue, cool star will be red. It was just the beginning. But nevertheless, let's see if I have here. It's a nice one.
Stars classification. Welcome to the short lesson about the spectral classification of stars. 1. O stars. They're the brightest ones, the youngest ones, the hottest ones. They're associated with the blue color. 2. B stars. Pretty much as O stars. They're very hot, very big, also blue. 3. A stars. Temperature of about 7,500 to 10,000 Kelvin. They're smaller than B and O stars. 4. F. Smaller than A stars, colder. Color temperature, yellow, white. 5. G stars. Pretty little stars like our sun. 6. K stars. Tiny stars. Color, light orange. 7. M stars. Orange, red stars. The smallest ones, the coldest ones. They own a lot of metals. Here's an easy way to remember the letters. O, be a fine guy, kiss me. Stars classification.
Lovingly. Now you have lovingly. Because it's not lovingly, you know what's the point. Okay, so then came Max Planck with one piece of the puzzle, and he was able to match color and temperature. So now, not only did we have the star, the classification, O, B, A, and so forth, but you also had the temperature, because he found a way, and he worked on the work by Wiens law. Okay, here, if you have the peak wavelength, so if you have the color of the star, you can find its temperature. So red star, we have a lower temperature. Yellow star, higher temperature. Blue star, very large temperature. So what's the point? The point is now they have one more piece of the puzzle solved. Okay, so now they have, so you have classifications here, but now they can have the temperature. O star is blue, they can find exactly the peak wavelength, so they can find its temperature. M star is red, so they will find its temperature. So it's one more step toward understanding what's going on. So the thing that was left to understand, why is it that you have this QR code here for this temperature? What is it that for this temperature you have this QR code? Why is it that for this temperature you have this QR code? So the missing link was to link temperature and QR code. And that came from a surprising place. The one who understood that, okay? And he's kind of, they forget about him, but he was a genius. I will tell about him. So anyway, black body radiation, you already understand that anything that will emit radiation, like a star, human body, Earth, right? The peak wavelength, the color is linked to temperature. It's an inverse law, okay? Okay, well, that's the same story of black body. So for example, we have, so that will be our sun. Our sun is about 6,000 K. It peaks in the green. And then if you have something that will emit infrared, it will peak in the infrared. And the peak wavelength will be infrared. And if you find this area, you can find the energy output. Okay, not only that, you see, so this is called spectroscopy. Not only you can find the peak wavelength, like the sun, but you see that you're going to miss some wavelength. So this is the QR code, right? This is the black lines superimposed to the rainbow. And as I've said before, if you look at that QR code, you can find the chemical composition of a star. Still, we are missing an explanation. Why is it? Okay, why is it that you have these QR codes? What's going on there? Okay, so why is that happening? That becomes that takes to quantum physics, and that was explained by Bohr, like 1913, so the beginning of quantum physics. It's very simple to understand. Let's say this is the core of your star, so radiation is being emitted. When light is going through the atmosphere of a star, some wavelength will be absorbed, okay? And then it will be burped out in another direction. That's why you have this black line. So why is it that those wavelengths are absorbed? Because electrons will use it to go high. Okay, they get high. They go to a higher level of energy, and then when they relax, they're gonna burp out that light in another direction. So that's the physics behind it, okay, if you want to understand what's going on. So for example, hydrogen, the electrons here are on energy level, and when they absorb some wavelength, okay, not any wavelength, only the wavelength they like, they go high. They say, this one I like, go high. When they relax, they burp out the photon in another direction. So that's how we have QR codes. But still, not fully understood what was going on. Why is hot star have this kind of QR code and red star have that kind of QR code? And the explanation came by was a genius, Saha, Meghnad Saha. I don't know if I say it right. He was a Bengali physicist, astrophysicist. So I don't know if you heard of Bengal. If you want to connect to geopolitics, it used to be British India at the time of colonialism. So India belonged to England, and Bengal was part of this empire. 1947, India got its independence, and then India split from Pakistan because you had the Hindus and you have the Muslims, and they didn't get along at all. right? So most India is Hindus, and the Muslim will go to Pakistan or stay in Pakistan because it was mostly Muslim, and the people, the Hindus who live in Pakistan, moved to India. So that's how Pakistan was born. Okay, 1947, something like this. It's interesting. And then you have East Pakistan and you have West Pakistan. Anybody knows what East Pakistan became? Bangladesh, because they didn't get along. Right? So you have West Pakistan, East Pakistan, you have India in between, and then there was a civil war, lots of casualties, and they break free, and it became Bangladesh. That's how Bangladesh came to be. They break free from Pakistan. And even today, you have a lot of issues going on, a lot of death that people don't talk about, never talk about this part of the world. But in Bangladesh in 2023, there was a coup d'etat, and they kicked out the lady in charge, and now you have a lot of unrest. Okay, so anyway, he was from there, Bengal, and so it was British India, and he was a genius, and he understood what was going on. Okay, so what was going on? He built on quantum physics. He understood that very, very hot stars have enough energy for helium electrons to break free. So in very hot star, you're going to have a lot of lines of helium. So that will be class O and B. And then he understood that A star, which is a little bit cooler than O star, going to have just enough energy for electrons in hydrogen to get high. That's enough energy for electrons to go to a higher level of energy and then to come down. So that's why you're going to have a lot of hydrogen line. And then as you go cooler, for example, if you have very, very cool star, those stars in the hot gas inside them, they don't have enough energy for hydrogen to be involved. So electrons from hydrogen cannot get to a higher level of energy. It will be only molecules. So that was a very, very breakthrough because he was able to link absorption lines and temperature. And he was using quantum physics, right? That was being worked by Bohr, for example, right? Bohr said that in an atom or molecule, you have energy level. Okay, so big breakthrough. People forgot about him. I think he became a politician. And so that was in 1920. Okay, he made that link, and then everything was consolidated, summarized by Cecilia Payne in her PhD. So she was the first woman to have a PhD from Harvard University. She had her BS from Cambridge University. And interestingly, she understood very well what was going on. So she was able to apply his equation to stars. So she's the one who, I don't know if I have the picture again. Yeah, she's the one who said, okay, all stars will be at that temperature, and we'll have this QR code, A star, you see, that will have this temperature, this star here will have that temperature, and this QR code. So she applied the idea of Saha to stars. And interestingly, her advisor was the very famous Norris Russell, who had developed HR diagram. So understanding this, she said in her PhD thesis that stars were mostly made of hydrogen and helium. 75% hydrogen, 25% of helium, more or less, right? She came up with that. And he said, shut your mouth. You're going to be in trouble. It's going to ruin your career. It was met with skepticism. So they didn't believe her, but she stuck to it. She published her thesis, and turns out she was right? So morality is stick to your idea, even though everyone said it doesn't make sense. It actually did make sense. So she was right. So thanks to those two persons, that's how we solved the mystery. Okay, so now here we understand what's going on. All those stars here are classified into classes. Oh, boy, fine guy, kiss me lovingly. And then you have the colors here, okay, because that means hot star will be blue, will peak in the blue. G star will peak in the green. So that's going to give you yellow or white. And then M star will peak in the red. So that will be red star. Okay, so here you have the temperature. Okay, and here you have the explanation why do you have this QR code. So the red star are mostly has a lot of metals, so molecules, right? So it doesn't take much to excite those molecules. So you're going to see a lot of lines for those molecules, but not much lines for hydrogen or helium. Okay, so again, the HR diagram now could be fixed. So you still have the classes here and the color, but now you have the temperature. Okay, so nowadays, if you look at a star, you don't need Wiens law anymore, right? You have the star, you look at the QR code, and you say, oh, it's a S star. Once you know it's a S star, you know exactly its temperature. You can plot that star on the HR diagram, and you know its luminosity. So it was a big, big breakthrough at the time. It's a difficult topic to teach to students who didn't take physics. So I hope I made my point. I try to do it like in a nutshell. So I hope I have succeeded. Anyway, what else? HR diagram. Okay. 27. So you have a lot of diversity in temperature. So you can have very hot star. And hot star we have a very short life, maybe 10,000 years to live. It's very short. And then you have very cool star who have a very long life and who are very small. You even find brown dwarf. So as I've said before, brown dwarf are failed star because we don't want to hurt their feeling. So we don't call them failed star. We call them brown dwarf. But that means they are very cool. Sometimes just the temperature of hot tea. They are so cool. So they will be in a special class. So, oh boy, a fine guy kiss me lovingly, tenderly. Yo, so Y. And T and Y will be brown dwarfs. Okay, so big diversity in the colors. Color. And I have a nice video, only if I can find it. Color temperature. Here. You have to pay attention. Are you paying attention here, everyone? Because it goes fast. Maybe I can slow it down. Okay. Ready? You increase the temperature, the color is going to change. That will be our sun, 5,000. Blue, very hot. Very hot. So it goes very fast. So again, same idea here. Here it's a nice picture because you see that the mass, the size of star is about proportional to the mass. So when they are on their main sequence, the size is not going to change much. And it's going to leave the main sequence. Our sun will leave the main sequence and become a red giant and start fueling helium into carbon and magnesium, for example, if you have a blue star, when it's going to run out of hydrogen, it will become a super red giant like Betelgeuse, or a blue giant like Rigel, and they can swing back and forth. Okay? When our sun will be done burning whatever it is to burn, it will burp out its outmost layer in a planetary nebula, and it will become a white dwarf here. So these are for the white dwarf. Here you have the red giant, but all the stars that you have here are on the main sequence, and they are burning hydrogen into helium. Here they live forever, and here they have a very short life because they die hard. And no,